Welcome back. So now we want to look at an ideal Bose gas. We look at an ideal Fermi gas, and now we want to look at an ideal Bose gas. Recall that the variable eta takes a value +1 for a Bose gas and for a gas which is made up of bosons, and for bosons the wave function that we have are symmetric wave functions. Not only that, in the Fermi gas we saw that Nk is restricted to be either 0 or 1, which is essentially the Pauli's exclusion principle that states that not more than one particle can have the same quantum number, which means not more than one particle can occupy the same single particle level. Bosons do not have these restrictions, and therefore these have some interesting implications, as we'll see later on when we go further into this. Most importantly, you can see that since they do not have these restrictions, more than one particle can come to occupy the single particle level. And therefore it becomes interesting that as you keep on decreasing the temperature, the zero energy state is very, very special, where you will see that all the particles go and sit over there. But this is what is called Bose-Einstein condensation, but this is not really a condensation in a real space. It's a condensation in the momentum space. We will look at that later on. Right now, our starting point is the grand canonical partition function, which we had written down, and which simply is minus k ln 1 minus z e to the power minus beta epsilon k. Now the particle number, if you recall, was sum over nk, and the average value of nk is del beta epsilon k minus of ln q plus. And if I do this, take this derivative, then essentially I am taking the derivative with respect to one energy level, and therefore in the whole sum that you see in this ln q plus, only one energy level will be picked up, which means you are going to have 1 minus z e to the power minus beta epsilon k then minus z e to the power minus beta epsilon k, and then del beta epsilon k of minus beta epsilon k. So that gives you z e to the power minus beta epsilon k divided by 1 minus z e to the power minus beta epsilon k, 1 minus z e to the power minus beta epsilon k, so that you come up with the expectation value nk is equal to 1 over z inverse e to the power minus beta epsilon k minus 1. And this expression then takes the form n is sum over k 1 over e to the power minus beta epsilon k minus mu minus 1, right? Now clearly you know that the restriction is nk is greater than 0 less than equal to the total particle number. And it follows that if I look at this, now since I have this restriction that the occupation number in an energy level must be greater than 0 less than equal to n, right? It cannot be more than n, of course, because you have a total of n number of particles. This effectively means, if you look at this expression carefully, this effectively means that epsilon k minus, and this means that mu must be less than epsilon k. But this is true for any energy value. So what should be the restriction on mu then? Then one has to look at the energy levels and look at the lowest bound of this. And the lowest bound of this corresponds to epsilon k is equal to 0, the zero momentum state, because these are free particles, right? So I know that epsilon k is equal to h squared k squared over twice m, right? So therefore, it follows that since this restriction must be valid for any of the energy levels that I am considering, it must be also valid for the lowest energy level, which is mu epsilon k equal to 0. Therefore, it follows that for a Bose gas, mu is less than 0. The chemical potential of a Bose gas is always less than 0. Which means that the fugacity must be greater than equal to 0, less than equal to 1. Now, this mu less than 0 is essentially it's a reflection of the fact that the bosons feel an attractive potential. When we did the canonical formalism with bosons, we saw that the pair interaction was attractive, right? So, it is simply statement of the fact that the chemical potential is less than 0, and adding more and more bosons to the ground state does not cost you any more energy, right? Now, how do we proceed? Well, the idea is simple. We have done it several times. So what we write down is we replace the sum. We assume that we have a thermodynamic system, which means it's a macroscopic system with a large enough box length so that my energy eigenvalues epsilon goes as 1 over L. The modes, the discrete k modes that we saw, that kn is 2 pi n over L. It goes as L, 1 over L. And consequently, all the energy spectrum looks a continuous spectrum. So that the discrete sum over k, which is this, can now be replaced by a continuous sum, which we did for the fermionic system when we looked at ideal Fermi gas, and that goes as d cube of k. Now here we did it in the Fermi for an ideal Fermi gas. We want to write down in a slightly different way. There has to be a g factor over here that comes from the degeneracy, the internal degeneracy, internal degrees of freedom. 2 pi whole cube times gv, this becomes 4 pi k square dk. But h square k square is twice m. H square k square by twice m is epsilon. So it follows that twice k dk is twice m over h bar square d epsilon. And the first equation also implies that k is twice m epsilon over h bar square raised to the power half. So I have gv over 2 pi whole cube, 4 pi, and then I take a 2 divided by 2 and multiply it by 2, so that this becomes 2 pi and I have k 2k dk. 2k dk is straightforward, twice m over h bar square d epsilon, and this is straightforward, twice m over h bar square half times epsilon half, and then you have the integral gv over 2 pi whole cube times 2 pi. So all the constants come outside the integral, so that I have gv over 2 pi whole square, and then I have twice m raised to the power 3 by 2, and I have h bar whole cube, right? Integral epsilon half d epsilon. This is further, it can be simplified by noting that h bar is h over 2 pi, so that I have a 2 pi whole cube, and this is 2 pi whole square times 2m raised to the power 3 by half, divided by h cube integral epsilon half d epsilon, so that this sum over k now goes to 2 pi gv over h cube times 2m 3 half integral epsilon half d epsilon. The reason I wanted to take this particular approach is that you'll see that both of them are equivalent, but because I wanted to highlight something over here, now this I can write down g epsilon d epsilon, where g epsilon is the energy, is the density of state, which means the number of energy levels lying between epsilon and epsilon plus d epsilon is g epsilon d epsilon, and for this particular case this is going to be, we'll just write down this as epsilon to the power half. It is very interesting that this quantity depends on the dimensionality of space. Please note that where does it come in? It comes in over here. I have a three-dimensional system, therefore I have taken d cube k. If you had taken two-dimensional system, you would have d2k, which would mean that this is k dk. And if it is k dk, you immediately see that g epsilon is constant, because half k, sorry, not half k dk, because just go back over here, this part, when you had for a two-dimensional system, I'm not worried about the constant factor, but I'm just worried about the one which is under the integral. You would have k dk, which you can write some constant times, let's call the constant as c k dk, which is nothing but c by 2 d epsilon, 2k dk, and this is d epsilon, and therefore it follows that g epsilon is going to be constant for when you're looking at a Bose gas, or when you're looking at a free particle gas, whether it's a fermionic system or a bosonic system, the density of state is constant in 2D. In 1D, this is just going to be dk, right? The sum over k will just go over to some constant times dk, and dk, if you look at the relation between the energy and the momentum, I have dk going as d epsilon by k, so that this integral will go as integration d epsilon over k. Some constant factor is always there outside, but that is not something which you have to worry about too much. But the idea is now k goes as epsilon to the power half, so that your g epsilon goes as epsilon to the power minus half. What is interesting to note that here the density of states, the number of energy states, g epsilon at epsilon equal to 0 is 0 in 3 dimensions. There are no energy levels at this particular energy. That's what my density of states tell me. In contrast, if you go to the two-dimensional case, then you see that all throughout the energy spectrum you have a constant number of energy, density of energies. So wherever you consider your epsilon to be, whether it is between 0 and d epsilon, or it is epsilon and epsilon plus d epsilon, the number of energy states are the same. In contrast, for a one-dimensional system, 1D system, the number of energy levels near epsilon equal to 0 diverges. That is very interesting. So we will see what does it mean later on when we look at Bose-Einstein condensation. Coming back to this now, I have sigma over k that goes to integration of g epsilon d epsilon with g epsilon given by gv twice pi gv over h cube twice m raised to the power 3 half epsilon to the power half, right? But note that even I am considering that my system is macroscopic, so that energy levels are continuous. In reality, this is not the case, because you still have Kn scaling with as 1 by L. So you have a very tiny difference between the two energy levels. But epsilon k at k equal to 0 is 0. So there is exactly one energy level which is there at the zero momentum state. But this clearly doesn't seem to be the case, which we have already highlighted out. While going from this to this, we clearly see that there is a problem, because g epsilon goes to epsilon to the power half. The discrete case, when we look really at the discrete case, we see that even at k equal to 0, the zero momentum state, there is one energy level. But the moment we replace this sum by a continuous integral over the density of state, we see that at epsilon equal to 0, there is no energy level, because g epsilon is 0 as epsilon tends to 0. So therefore we have to be a little bit more careful in our analysis. So what we have to do is we have to separate out the zero energy level, the zero momentum vector, which we do it over here. We look at this expression over here, and then we see that I can write down this sum as ln q plus as minus sum over k ln 1 minus z e to the power minus beta epsilon k minus g ln of 1 minus z. There is no volume factor which comes in over here. You are just looking at one energy level, and that has a degeneracy, internal degrees of freedom, which is usually the spin, which gives you the degeneracy level g, right? Similarly, I can take a look at the average, this quantity over here, average occupation number, which was nk as 1 over z inverse e to the power beta epsilon k minus 1, and the total particle number was sum over k. This sum does not include the k equal to 0 value, because that's the value I have included over here, and I can take care of this way also over here. Z inverse e to the power beta epsilon k minus 1 plus 1 by, there's going to be a degeneracy factor of g, one by z inverse minus 1, where I have set epsilon k is equal to 0 both here and here to get the last term. So this gives me sum over k 1 over z inverse e to the power beta epsilon k minus 1 plus gz 1 minus z, right? Now the question is, why do we want to take care of this k equal to the zero momentum state specially, right? We didn't do it for a fermionic system. Now for a fermionic system, we were kind of saved by the Pauli exclusion principle. I'll explain to you why we have to do it over here. Now the idea is, in order to go forward, as we have seen, that we convert this sum into an integral over there using the density of states. But that integral clearly ignores the zero momentum state, because there is no energy states lying at that particular value, and the value epsilon equal to 0 or in the neighborhood of epsilon equal to 0. Therefore, that is the problem. In a fermionic system, even if you have a large system which had a large volume V and a particle number n, Pauli exclusion principle would tell you that you can only have one particle in that energy level. So you are at most ignoring one out of n. But bosons do not have that. In bosons, for bosonic particles, more than one particle can go and sit at any energy level. So therefore, if you do not have sufficient thermal excitation to excite the particles to higher excited levels, all of the particles would like to go and sit at the lower and lower energy levels. So if you keep on decreasing temperature, they are going to go and sit at this energy level. So it can happen that a substantial number of particles are sitting at epsilon k equal to 0, the zero energy level, but your partition function as well as this expression does not take that into account, right? Because your G epsilon vanishes as epsilon goes to 0, and it is therefore precisely that you have to take care of this very, very carefully. So let's move forward. Ln q plus is minus the sum over k goes to integral G epsilon d epsilon, and then I have ln 1 minus z e to the power minus beta epsilon. Now we do not talk about epsilon subscript k, g ln of 1 minus z. So let's see, what was G epsilon? G epsilon was minus twice pi gv over h cube twice m raised to the power 3/2 integral epsilon. So we write down d epsilon to the power half ln 1 minus z e to the power minus beta epsilon minus g ln of 1 minus z. So this means minus 2 pi gv. We are now very, very familiar with how to handle such integrals. We do an integration by parts where we take the log as the first function, so that this becomes ln 1 minus z e to the power minus beta epsilon, and I have epsilon to the power 3/2 divided by 3/2 minus integral d epsilon to the power 3/2 divided by 3/2, and then I have derivative of the log this function with respect to epsilon. So I have 1 minus z e to the power minus beta epsilon minus z e to the power minus beta epsilon, and then del d epsilon of minus beta epsilon. We close the bracket over here, so that this becomes twice pi gv over h cube twice m raised to the power 3/2. This vanishes between 0 and infinity. I don't have to worry about it. This is minus integral d epsilon to the power 3/2 divided by 3/2 minus z e to the power minus beta epsilon 1 minus z e to the power minus beta epsilon, and then dd epsilon minus beta epsilon is just minus beta, so that this minus and this minus gives you a plus, and this minus and this minus gives you a plus, so that you have 2 pi gv over h cube twice m raised to the power 3/2. I have this as 2/3, and the beta I bring outside, 2/3 beta, and then I have integral d epsilon. Let's put the limits so that we don't miss anything later on. I have epsilon to the power 3 half. I have z e to the power minus beta epsilon 1 minus z e to the power minus beta epsilon. Our final simplification, 2 by 3 beta 0 to infinity d epsilon is epsilon to the power 3 half divided by z inverse e to the power beta epsilon minus 1. Now do not forget that I also have this term. So I have a minus g ln minus 1 minus z which is being carried forward, right? I can also be a little bit more smart. I can substitute x equal to beta epsilon and I can rewrite this expression as twice m raised to the power 3 half 2 by 3 beta. This is beta to the power 3 half and I have 1 over beta to the power 3 half 1 over beta times epsilon, so that I have beta to the power minus 5 half. A 3 half that comes from over here and the beta alone comes from over here, and I have 0 to infinity dx x to the power 3 half divided by z inverse e to the power x minus 1 minus g ln of 1 minus z. Sorry, let's write down. This is my grand canonical partition function for a bosonic ideal Bose gas. Well, now this is the part which looks extremely complicated. Let's see, can we see whether this gives us something interesting? Because see, the whole description or derivation of this, the canonical partition function, essentially has started from the fact that this integral I can convert it into d epsilon g epsilon. And the idea was that when we did the fermionic system, we did it in a slightly different way. We essentially wrote this as in terms of dk itself times some function. I think it was 2 pi to the power half lambda t times k, right? So yeah, so x was beta h bar square k square over twice m, and so that x k was 2 pi half raised to the power but divided by lambda t times x. Something like this was there, and we had used this particular approach. Now I said that both of them are identical. You're going to get the same thing. I have just used different approaches for the two different cases so that you are familiar with both of them, how you want to proceed, right? So now 2 pi gv over h cube twice m raised to the power 3 half 2 by 3, this gives you 1 over beta to the power 3 half. So here let's bring a 3 by 2 factorial divided by 3 by 2 factorial. So we will put it over here itself. I have a 3 by 2 factorial and I have a 3 by 2 factorial, and the 3 by 2 factorial in the numerator I include over here, this times 3 by 2 factorial. So the expression that I'm looking at is simply this. Now this quantity 3 by 2 factorial is 3 by 4 square root pi, so that I have 2 pi gv over h cube twice m 3 by 2 2 by 3 3 by 4 square root pi 1 over beta to the power 3 half. So you should already get a feeling where we are going. So this should be, now let's cancel. The cancellation is 3 gets cancelled. This gives you 2 and this gives you 2. Remember, this is 2m raised to the power 3 half. Okay. So these 2 and these 2 cancels with the 4. And this pi and this square root pi gives you a pi to the power 3 half. So that which couples with this 2m raised to the power 3 half to give you GV 2m pi raised to the power 3 half. And then I have this beta to the power 3 half and I have h cube, which I can easily include as beta h square. And if you remember your de Broglie wavelength, which was beta h square over 2m pi half, then this quantity is GV over lambda t, which was exactly the prefactor we had when we looked at Fermi integrals or fermionic systems. So my partition function becomes ln q plus is GV over lambda t integral dx 0 to infinity 1 over 3 half factorial x to the power 3 half z inverse e to the power x minus 1 minus g ln of 1 minus z. Now clearly this is the part which looks very familiar. And if you recall, fm eta of z was 1 over m minus 1 factorial 0 to infinity dx x to the power m minus 1 z inverse e to the power x minus 1. This was how we had defined the function, and therefore this is f of 5 half plus z. So your grand canonical function takes the form GV over lambda t f 5 half plus z minus g of 1 minus z. Right? Average expectation number was 1 over z inverse e to the power beta epsilon k minus 1, and we separated the zero momentum state out so that we have z inverse e to the power beta epsilon k minus 1 plus g z 1 minus z. This means that if I go to the continuum limit, I have 0 to infinity g epsilon d. So one has to first write down the measure d epsilon g epsilon 1 over z inverse e to the power beta epsilon minus 1 plus g z 1 minus z. This again is 2 pi gv over h cube twice m raised to the power 3 half 0 to infinity d epsilon to the power half 1 over z inverse e to the power beta epsilon minus 1 plus gz 1 minus z. Right? And I have 2 pi gv over h cube times twice m raised to the power 3 half. I will again substitute x equal to beta epsilon here, so that d epsilon is 1 by beta dx and epsilon is x over beta, so that I have beta to the power 3 half, and then I have 0 to infinity dx x to the power half z inverse e to the power x minus 1 plus gz 1 minus z. One needs to look at this factor over here again, and this is just a repetition of what we did earlier, but let's just do it very quickly. Multiply and divide throughout by half factorial, so that you will have this particular quantity will give you 2 pi gv over h cube twice m raised to the power 3 half square root pi over beta to the power 3 half. So this has to be square root pi by 2, which is gv. The pi and square root pi will go inside over here to give you 2m pi raised to the power 3 half. H cube and beta to the power 3 half can be combined to give you beta h square, so that you have gv over lambda t. So this total particle number then becomes gv over lambda t, and this integral is very familiar to me, in the sense I know that we use this thing for m equal to 3 half, and therefore I have f of 3 half plus of z plus g of z 1 minus z.